Okay. Okay. So the idea of a shallow neural network is to get rid of the linear model where we have some input x and x2, which goes into a single layer network pretty much, which was for logistic regression is wx plus w transpose x plus b, and z is equal to that. And then so input x goes in that, and that produces a, which is equal to the sigmoid of z, and w is, and then this produces y hat, and w right now is a x by 1 matrix or vector, which means for every single x there's going to be a w, right? So you get the point. It's going to be like this, where it's just going to be w1 down to wm by 1. So as opposed to this linear model, if we have a function that is more complicated, say we have points like that. Actually, let me say we have our points like this. To fit a model like that, we need to get rid of linearity. Okay, so a shallow neural network is gonna have usually 2 or less layers or hidden layers. So that's why we call it a shallow neural network. And what this is gonna look like? We have some input x1, x2 down to xm, and we're gonna have multiple linear functions where z is gonna equal to w transpose x plus b, and this can go down to whatever. We can have as many neurons as we want. I recommend starting with 2 or 3. So this is 3, but it can span down to 5 or 20, whatever. So each input goes into this model, goes into different weights and bias model. And one way you can represent this is you can say W superscript 1, representing this is the first layer W, the first neuron. So first layer weight, second neuron, superscript 1, third neuron, and same thing with this 1, 1. I'm not gonna keep going, but you get the point. And then every single input is fed into a different linear function. Now all your W's are set to random values, very low random values. One way you can do that is you can say random dot randin, and you can say it's an n by h. Sorry, n by h. What the fuck? N by h and a n by x vector, where nh is your neurons and nx is obviously how many inputs you have. So xm, how many inputs you have. So now, unlike regular logistic regression, your W, I'm going to make this capital, your W is going to have a bunch of random numbers set. By x, so row x, so this should be the other way. So let me do this again. So this might be 0.5, 0.3, 0.1 by your x, however that may be. So 1, 2, 3, right, whatever. So now you have multiple of these linear functions as opposed to logistic regression, and they're all going to be set to random values, and you're going to want to multiply by 0.01 in your code. So it's going to be a very small number because random is going to be like 80 or something. But if you multiply 80 by 0.01, you're obviously going to get a number closer to 0. And the reason we want that is because if we have really large numbers on gradient descent, we're going to have to take a lot more steps to get to the bottom of the slope, right? So then this is fed into A. Actually, we can just say Z1. This is Z1. So first layer, first neuron, first layer, second neuron, and so on. And then we can say Z2. It's better if you call these A, but just Z right now is fine. Where Z2, second layer, and first neuron is going to equal to W. Okay, sorry. And that's going to be W2. So your second layer is W. And just W2 is enough. This isn't going to span whatever, you get the point. It's gonna, and that's gonna be multiplied by Z1. So every single neuron's output plus B2. And don't forget what's it called? Wait, hold up. Oh yeah. Oops. Okay. So this should not be Z1. This should, let's just say A1, where A1, I drew this on my paper, I just messed it up, where A1 is some activation function applied to Z1, and same thing here. I'm not gonna rewrite it. A1 1 obviously, and then this is gonna, oh, running out of space. Okay, so this is gonna go to and then we're gonna take the sigmoid of A2. That's a 2 right there. Where A2 oops, sorry, not A2. I don't know why I did that. I meant Z2. So what happens is we do Z1 is equal to this. So X is inputted into this. This is calculated. Where W is a vector of a bunch of numbers set to a random value. Then what's it called? We take the activation function of that. At the activation function G might be either ReLU, tanh, or leaky ReLU. When you don't know what to use, either use tanh or ReLU. Leaky ReLU is not necessary unless you have a lot of x variables that are close to 0. And the reason for that is the ReLU function is like this. Oops. Can't even draw a straight line. Okay. So when you have a number really close to 0, obviously gradient is going to be, or your derivative is going to be really low. And tanh is like tanh is like sigmoid, but it's not like sigma. It's not sigmoid, so it's -1 instead of 0. So you go from -1 to 1. infinity. Oops. Okay, that is the worst line ever. There you go. So you can use regular tanh, whatever. So just tanh, for example. I want to highlight this in red. So pretend this is tanh. We do this. We take the tanh of this, and then we multiply W2 by the result of the tanh of this plus our bias, and then we take the sigmoid of that result, which obviously gives us y hat, or our prediction. Also, if you're confused on what the point of all this is, instead of just regular logistic regression, is if we have a more complex data set, so I'm going to do this in this green box here. Alright, if we have a more complex data set where our points are not linear, well, technically this is linear, but you get the point. Where our data is spread out like this, but we don't have a linear function, we need to introduce non-linearity to actually be able to fit a better line. So let's say this y hat, so it can be able to fit a line approximately accurately, right? So our line isn't going to be perfect because we don't want to do overfitting. So we want to get a line as close as possible, and this business right here, when we multiply, when we have more weights, and we multiply that by the result of a non-linear activation function, that obviously introduces non-linearity. So for more complex data sets, we want to build neural networks. I don't consider logistic regression a neural network, but people call it that. So also, yeah, your W2, W1, and 2 are both going to be set to random values. Your W1 is going to be set to random values, but it's going to be an n by h by an n by x. But this one is just going to be okay, sorry, this is going to be a 1 by so let's just say this is 3. Let's say we have 3 neurons. This is going to be a 1 by 3 vector, and the b, you know, you get the point. So also I forgot to say b1 here. b1 is going to be just a 3 by 1 vector.